Very exciting.
All right, we are live.
I can't see it on YouTube yet.
YouTube OBS tells me we have excellent quality.
Aha, there we are. Just had to reload.
Do you also hear yourself?
No, I muted the. Oh wait.
I'm just saying, is your voice being recorded? Yes.
Yeah, I can hear myself. I think I'm as loud as the music though. Did you make the music quiet in OBS? So maybe you made the music quiet wherever
Yes.
your player of the music is.
Okay, so I'm gonna increase then. Let me first make it more quiet in.
Yep.
Much more quiet there. Turned it all the way up now. On.
You updated the background, but it says Meta Matze.
Oops.
It's pretty. Oh, now I can hear. Now say you have to say something.
Hello. Test.
Yeah, I think I'm definitely louder than you are. Yeah.
Okay.
So you can make the desktop slightly quieter.
Okay, how about now? Now.
Test, check 1 2 1 2.
I think.
Yes.
Yeah, if I look at this, I think like if I look.
Okay,
at
that
the
sounds
volume,
good now.
You're still a tad louder than
Sure.
I am.
Then quiet me down.
I think now it should be quite equal. Can
Okay.
you say something again?
I guess Nicholas can let us know in chat.
Yeah. Do we have Nicholas in chat?
Yes.
Today I don't have the chat open, so you'll need to keep me updated. Is the background music okay or not audible?
I can't hear music anymore.
Okay. I'm putting it up a bit.
That's too loud.
Okay.
Slightly quieter. Oh my god, the levels. Yeah. I think we're here. I'm still very loud, Nicholas says. So.
Okay, Matthias is still very loud. Okay, then let's tune you down further. How about now? Can you say something again, Matthias?
Check. You also have to say something so I can double check on my end.
I would say you're still a little louder, but
just go by your feeling or by the levels you see.
Okay, then say something again.
Yeah, okay. I think we're on the right track now. Okay, Nicholas says okay. Thank you for setting this up with us, Nicholas.
Yeah, thanks for helping us with that.
Then I'm going to mute my tab so I don't hear both of us twice. Great. Okay.
All right. I'm just gonna do a very quick setup for the demo that I'm about to do.
Mm-hmm. I can on the side tweet.
Yes.
Tweet some more. Tweet some again. Mastodon again. Blue Sky again. LinkedIn again. I don't know what else is there.
Yes.
Quote retweet. So How's everybody doing in chat? I don't know if there's more people in chat. I have the impression that Fred's voice is lower again. I mean, that's because he's not saying anything, but I don't know if there's more people in. Let me check. I have.
Okay.
I guess we can adjust like whenever someone tells us in chat.
Yeah.
Yeah, just let us know if we need to like still adjust even further. Okay, it's fine now. Never mind. Okay.
All right.
Well, if it isn't at some point, let us know.
All right. I guess we have a couple folks in chat, so I guess then we can get started with that demo that we promised on Twitter.
Let's do it.
All right.
I'm curious to see it.
I think Matthias is seeing this for the first time live as well. So we've got something pretty exciting cooking, which is this. So basically, it's been possible to add distributed tracing IDs to profiled stacks if you used instrumented profilers. So like if you use the pprof profilers in Go, for example, you could add this like pprof.do instrumentation, and then you could add, for example, the trace ID to your stacks. And that's neat, right? But in the Parca project, we're all about doing kind of not the we want to avoid using instrumented profilers as much as possible, and as much as possible get data from eBPF. And so this was kind of an experiment that I just started on last Friday, actually. And it quickly kind of tumbled into, actually looking like it was going to work. So this is the pull request. As you can see, I opened it 2 hours ago. And what I'm going to do now is I'm going to have a quick, like a tiny demo here that just, has these go routine labels set. So that's how we're doing this. So the target process does still need a tiny amount of instrumentation, but the point is that we don't have to use the instrumented profilers to do this. And I think this is an okay trade-off here, because distributed tracing needs instrumentation fundamentally, right? And so that's why I think I feel pretty good about this. Theoretically, we could also try to read the distributed tracing ID, from the incoming requests or something like that. But I think this is already something pretty exciting that we weren't able to do so far. So I think it's pretty cool. So to show you that this actually works, right? So like I said, I have a tiny application here. Let me show you the code for this. It's super simple. So we just have, a main function with this like tiny wrapper around the OTel tracing library. Theoretically, we don't actually need this. We could also just do something like pprof do labels, and then I don't remember the exact interface, but it's something like this, and then do our work within this, and that works as well. So I think actually we're going to see more of that happening, so that people can say, there's this super frequent thing happening in my system, kind of similar to distributed tracing, and choosing what to sample there. So for example, I think in our infrastructure, I don't know how useful it would be to have the distributed tracing ID for every write request, for example, but I think it's super useful for every read request, right? And so I could see us doing more pinpointed instrumentation here on a per interaction basis, for example. So super powerful, I think. So I'm just going to start this example, produce a little bit of load here, and whoops. And I already have a Parca server and my Parca agent running on this like Linux machine in my network. And I have the Parca server here. And we can see, so we have our example binary. Second, it needs a second to symbolize, I think. This is actually a bug we just fixed on main. That unsymbolized profiles show as no profiles. But now we can kind of click one of these and say we want to group by labels. And now we can see we have these distributed tracing IDs. And we could also now go and use this tracing ID. Let's see, we don't actually, so I think this way we could do it, yeah. We could also, didn't think. That was strange. The right click didn't actually. Maybe this way then. So
more things to fix.
This way as well. This way as well, that we query by the distributed tracing ID, and this is, I think, gonna be the like most amazing user experience, because now we can view all the CPU time across all the services in our infrastructure for this one request, right? So we don't need to care about in which service did the CPU time happen, but we can see the whole icicle graph across the entire request path. So I think that's gonna be super powerful and enable even more kind of pinpointed profiling. I'm pretty excited about this. So yeah, that's the thing that we kind of been cooking lately, and I think we're gonna be writing a blog post and actually releasing this sometime next week. So please, keep a little bit quiet about this if you're on the stream, but now you're in the inner circle if you're watching this live or on the recording. So yeah,
nice.
That was. Yeah, go ahead.
Yeah, I'm just like kind of like trying to understand it myself, but like we basically need like all the services, they need to have distributed tracing, and they need to do some small amount of work to like propagate the trace IDs through the contexts. But like everything on the profiling side, that one comes for free if you have the latest Parca agent running at some point, because that one can just find the trace IDs on the stacks while it's profiling. So basically, if you already have tracing set up, this all of this comes for free, right? Like exactly. no extra instrumentation needed. Obviously, you need to store the data to some extent, but like this is like just a trace ID, so it's just storing a string, but like no extra thing required to instrument, no extra code changes needed if you have tracing.
You need to have like some entry point instrumented that once says for this Go routine, and every Go routine that this Go routine spawns, by the way, that's a Go internal, add this trace ID as a label to this Go routine, and this is what we go and search for in the agent. Now, obviously that is currently limited to Go, but we're already looking at other languages of how we can make this possible. But the super cool thing is now we can finally make this connection between distributed tracing and profiling data from eBPF. That was always the one where it's like, this is the one case where instrumented profilers sometimes can still have like an advantage, right? But finally now we're gonna be able to do this as well. So I think that's incredibly powerful, and obviously it's so much easier to then do this, right? You don't need to set up scraping, or you don't need to set up profiling in each individual application. It just works because it's already
you just need to do the tracing part, but nothing on the profiling side, right? Yeah.
Exactly. Yeah. And this is so simple. I can imagine this being already like by default in the like OTel HTTP library or the OTel gRPC library, because the point where you start for the first time a trace is where you'd want this instrumentation. And because it basically just needs to happen once for the first go routine, it makes sense to have that in those libraries directly. And then all of a sudden everybody will get it for free, right?
So cool. Yeah.
I think that's how I imagine this to pan out. The one thing that would need to be standardized within OpenTelemetry is what exactly do we call this label. But I think that's easy enough to agree on. Right now it's otel.profiling. Oh, not sorry, otel.traceid.
Yeah.
Simple enough, I think.
Yeah. One of those names should be agreeable to. Apparently I'm still a bit too loud, so if you wanna make me a bit quieter even further. And then we have Albert in chat as well, and Samara is in chat as well. So welcome. Good to see you around. Let us know again, if I'm still too loud for everybody else as well.
I just adjusted.
Let us know. Okay. Yeah, it's hard to gauge when I hear myself talking and check on the YouTube stream while you're talking, and so others, if you can let us know, then please do. That would be helpful.
Yeah. All right.
Awesome.
Now,
but yeah, super nice demo.
Now we can go on to the regular scheduled programming, which is today we wanted to have a look at. Let me close all of these. Today we wanted to have a look at optimizing a couple of common FrostDB queries. So there are a couple of examples of queries that we know we can do better. And two very concrete ones are when we're filtering and we have dictionaries in a column that we're filtering by, then it would make sense to only look at the dictionary for the filtering purposes, as opposed to doing the same thing over and over again for potentially, exactly the same value. And so there are a couple of optimization techniques that we could think of here, right? I think the first one would be, like I said, just running the filter on the dictionary, but I think there could be additional things where, if the column is not nullable and there's only one item in the dictionary, we actually can make an even faster decision, right? We could just say filter all or filter nothing. And then the last thing, and we'll see how far we get today, but the last thing that we could do on the same kind of in the same realm is working with run length encoded columns, where it's kind of wasteful to do multiple compare operations when we actually have a run of multiple of the same values, right? So again, a conceivable example here could be we have a single value that is run that whose length run is for the entire column, right? Why would we be doing multiple comparisons if we could just do one? At the moment, all of this is relatively naive in FrostDB. It just literally goes line by line and checks whether the filter applies. Now, as always with Let's Profile, I haven't looked at this code in a long time, except that I know that we don't have these optimizations. So it's totally possible that maybe we need to do a couple of refactorings to make this possible at all. I don't know. we'll see where the stream takes us. And I have about an hour and a half of time today, so we'll see how far we get. As always, totally unscripted. We'll see if it works or if it doesn't, and how far we get or not, right? Most of the time we managed to do something, but it's happened that we were not super successful either. That's how it goes.
Yeah.
All
Let's
right.
see.
So, first things first, our query engine is where this is gonna all take place. So we actually have this pretty handy kind of framework, let's call it, where, how did this work again? Where we can where we don't need the whole FrostDB storage, but can just test the query engine itself by kind of pushing Apache Arrow records directly into the query engine, pretending that these are coming from a storage. But this way we can just run some queries and actually benchmark much more realistically just the part where the filtering happens. So let's take one of these examples. And we'll do benchmark dictionary.
I'm wondering if it makes sense to just print some of those dictionaries on screens just so that people can get a better understanding. Because like I understand what you were saying, but I'm not sure it's the case for everybody on the stream.
Yeah, totally. We can do that. I'm gonna do that. I guess we don't really need anything else, but
just one.
Just one column.
Yeah.
Make this super simple. You might need to help me actually with the way we define this in Arrow. I've forgotten already.
I'm not sure what exactly you mean with
we need
this.
to somehow define a
dictionary. Like what dictionary? Good question. I think because we are using the schema PB column thing, we want to use some encoding type in there. Let me pull it up as well. We have example. I think probably just opening the example simple aggregation. Where do we have a good example for this? Schema.
I think it's somewhere here, right? Sample definition. Okay, so this is run length encoded. I wanted to just do
like something like this.
We can.
I don't think we. I think we only have run length encoded dictionary. Like the other way would be to not use the schema PB, but just create an error record in memory, basically.
That's what we're gonna do here.
Yeah.
So that's what's gonna happen anyway. So I'm looking for. I think it's just like. Okay, let's pull up the docs. So, yeah, okay, we want the most recent version. All the way at the bottom, there is array, I think. Is the way this works?
I mean, for arrow, you specify an arrow dictionary type with an index type and a value type.
Where do you see this?
I just know because I worked on this the last week. But yeah, I can help you type it out. I'm just not sure how like why do we need the schema, the FrostDB schema for this anyways?
That's a technicality of this framework because so the query engine,
yeah, there it is. The index type value type you just had up. Sorry, there's a delay between when I see things and when we say things.
Okay, so it's something like this then.
Yeah, exactly. This one. It has the index type and the value type. So exactly, you want the dictionary type, and within that you have the index and the value types.
Okay.
Gotcha. Yeah, something like this. Yes.
I think this is binary dictionary builder or something like that, right?
Yes, that's correct.
And we don't want to do an aggregation, we want to do a filter. Yeah, like this.
It's pretty wild how Copilot knows FrostDB logical plan syntax.
Yeah.
Very good.
Let's see, what do we want to do? Let's like count the number of rows we get out. So this, and then we expect make this in 64 as well. All right. Now, our old trick to ignore everything else, and then now I need to make sure we run this like 10 times. Looks like it is pretty fast.
We just have one value in the dictionary, no?
Yeah. Wait, we also actually forgot to do something. Everything in here we actually want to that, no, yeah, that's what I want. All right, here we go. That's better. Let me make sure I can do this.
Yeah, okay. The above looks pretty fake.
Now, let's see. Actually, what we want to do is to actually test the dictionary behavior. Let's add a bunch of items.
We can basically do like a FizzBuzz entry type of thing or something, right? Where we have like 3 values and we mod them or whatever.
Sure. Let's add like
your choice.
Like
I'm not forcing you to like implement FizzBuzz on the stream, am I?
I was just trying to think like how many values do we want to add to this. So I decided on like 8K values. I think that's roughly. I seem to remember there's some limit in FrostDB that we try to make row groups this size. It might be a multiple of this, but I think this is a good value to start with. And we can now. Oops. Okay, that of course makes sense. Oh. Okay. What's the correct multiple of 2? 1024, 2048, 4096, and that
8192.
8192. So all of the numbers.
Very close.
All the numbers I did were wrong.
I didn't know. I thought you were correct with the 8196, to be honest. Could have like told me that's a power of 2 number. I was like, yep. I think that's right.
I think that's the 8000 one is the one where I lose the ability to just name it off the top of my head. I think up until 4096 is where like 4 kilobytes, right? Like this is the number I type all the time, but then anything above that I don't type very often.
It's also weird because like the 40696 is just within within the like, but then it like goes over like the 100 step, right? Where it's like it then 81 something, and I don't know. That trips me. Yeah.
All right.
That was like very well explained.
Let's have a look at the CPU profiling data as well, just to be sure. That the matching is actually where the bottleneck is. Whoops, I think Matthias just disappeared.
Did I?
Yeah, because I think it opened.
Ah, yeah, it did. No, I can see it as well.
Wait. No, now you're gone again? What's going on?
Change the window in OBS or something?
Yeah, now you're back.
I can't see it yet. The delay is real. Oh yeah, there we go. Sweet.
Okay, so now we can go to our Safari window. Alrighty. So, system stack, some garbage collection, but here's our execution. So the physical plan, and here we go. This is our scalar expression filter. So looks like we've got dictionary, array, scalar equal. Maybe we already have this optimization. Let's have a look. Binary scalar expression.
But it is the get value index. I'm seeing that as a function call, so I'd be surprised. Or is that the correct one? I always mix up those two as well.
Okay, this is not equal. Let's start with equal. So let's see. So we've got the dictionary. Yeah. So this is something that we can do differently, right?
Yeah, exactly. So basically, what it means is that like if we have like the 8K values, it means that we still go over like 8,000 values, even though we only have a single value in the dictionary, right? So we have like it basically says 8,000 times A. So what we can instead do is let's just look at the A once and see if that is equal to whatever we want to filter for. And then I guess the like how are we going to do this like the other way around then like update all the filters, all the rows that don't match essentially or that match, right? Like but that's something we can do next. But it's kind of exactly that where we just want to look at every single value that actually is unique once and then figure out what that means for like 8,000 value rows in an array.
Yeah, exactly. Yeah. It does look like adding to the bitmap is also something interesting. So there may be an opportunity to, I think roaring bitmaps allow adding ranges. So there may also be another aspect here, which I didn't actually expect, and this is why we do profiling, where we can, add ranges and kind of figure out how long is the range of values where it's true, right? In this case, we're calling add n times, right, for each row, even though we have this run of all rows being not filtered out. So also an interesting edge case, right? That we're
for sure.
triggering here. And the other ones is our, looks like get value index. Okay.
Something is up with my audio again. Apparently there's a lot of echo if you want to look into that at some point, but I'm not sure where it's coming from. Do you hear me like just fine?
I guess, in your room there's a little bit of echo, but
I think it's more that I sound like a robot on the stream.
That's odd. I don't hear that.
Yeah, you don't hear it. I don't know what we can do about it. Am I like picked up twice or something weird? Like, do you have the call on open twice? I don't know.
You know what? Actually, that you might be picked up by the macOS screen capture and the Google Meet.
Something.
I think so. Let me mute the Google Meet entirely then.
Yeah, I think in OBS.
Yeah, I just did that.
Okay.
Now the Google Meet is completely gone.
Yes, it's gone. So I was audible twice. No echo. I still agree though that there's a lot of echo in my new room. We have like just plain walls. So okay, thank you. Thank you everybody for telling us in chat. That must have been pretty awful to listen to.
Sorry about that.
Glad we figured it out.
Yeah.
Okay, back to profiling.
We'll eventually get good at this live streaming thing.
Sure. We only been at it for 22 episodes. It's not our like work we make a living with, thankfully.
We do this on our fun Fridays in case anyone is wondering what we mean.
Not the profiling part, the streaming part, just to make sure.
Extra clear. All right, so how do we fix this? So we I think the way that we can then do this is what we'll have a bitmap for the entire dictionary. So we'll basically do exactly the same thing, but just once over the dictionary, and then we look up that index in the bitmap for each actual value to build the final bitmap. Does that make sense?
I guess so. I mean, we are in that case we're only skipping over comparing every single value, right? But like just adding values to just comparing integers, I guess it is at that point, right? Like that's pretty cheap compared to comparing strings, for example.
That's the idea. We'll see after profiling if it actually works, I guess, and after benchmarking. But
I was hoping maybe there's an even better shortcut we can come up with to just like, I don't know, reverse index the index to, I don't know. Let's go step by step.
So the good news is dictionaries can never be null entries in a dictionary. So this step is already gonna go away, which is, you know, not nothing. It's 50 milliseconds of, it's of like 1.24, which is a little bit less than 5%. So it's not huge, but you know, anything that we don't have to do is good. Actually, let me keep another copy of this code for later, because we'll need to do something similar. But for now, we're just gonna look at this. Interesting. I think also what I would like to do is move the switch out. I don't know if we can see it here, but there's gotta be, let me pull up Parca toolchain.
If you want to make your browser window a bit smaller, we can't see the right-hand side of the flame graph. I guess next time you open it.
Okay, yeah, makes sense. Yes. Here we go. There, I think this should be better. What I was pointing at is this part here, this flat part. I'm almost like, I would not be surprised at all if a significant portion of what is being spent in here is just that type switch that we need to do n times. We'll see if this holds true. Oops, what am I doing wrong? Go to Parca. Okay, Matthias was again.
I am a choreograph now.
So what was it? Binary scalar or something. Let's copy this. Here we oh, I called it. It's exactly like I said. Pretty much everything that is spent flat in this function is adding to the adding to this what is it again, the bitmap. This is actually interesting. That means that this casting is costing us a significant amount of CPU time, which makes sense. But that means that we should just be using a better type to begin with over here. So this is good, really good insight. And by the way, if you didn't already know this, we can do this in the Polar Signals Cloud product as well for your code. So you can see exactly all of this with your code. It's a super amazing feature. I use it all the time. But yeah, let's hold on. This is already the edited code. That's exactly the problem, and this doesn't happen on Polar Signals Cloud.
But yeah, I guess we can just use a UN32 in the loop for the index and not typecast it every single iteration, right?
Yeah, so let's see. Okay, so now it looks different. So adding. So I undid all the editing that I did, and now the code is actually the way it was recorded, right? So a decent amount of time is just spent in this for loop. That's something that we'll probably not be able to get rid of. This is a great one, right? Like this is the one that we don't have to do with dictionaries. But this type switch, as we can see here, is also using a decent amount of CPU time. And then finally, actually, the hold on. Why is any time spent here? Do we have a binary array? We only have a string.
Yeah, something's off. So. Did you do any changes in between running the
benchmark? Yeah, could be.
Yeah.
All right, then let me make sure that I rerun the benchmark one more time.
I'm going to try and find some instance of this on Polar Signals Cloud. Maybe that's even easier. You're not logged in, right? But maybe
No.
I can find one and share it on pprofme.
Okay, let me add the benchmark. No, because the benchmark didn't exist before. Add benchmark for dictionary filtering. Now we're gonna run this again. No. I need to figure out how this won't close Matthias, but huh, interesting. I don't know why that's happening, but for some reason, clearly we sometimes end up in this path. The data doesn't lie. It must be happening. Interesting.
Maybe, but it's only 20 milliseconds. I would assume that maybe it's the line above where it says, where it like actually checks, is this a array binary, and then skips over it, and it just isn't like properly shown, because like the case array string is also 20 milliseconds, right?
Yeah.
And then the actual comparison is 500 milliseconds. So I'm assuming it's probably just the switch case evaluating, and the line is actually incorrectly highlighted.
Yeah, I think you're right. I'm now quite curious. Yeah, we should. Someone who has enough time, investigate.
Please.
Investigate this. This is a pretty interesting one, I have to say. Okay, but we'll continue down now the path that we actually wanted to. We're gonna apply the changes that we did start. So now,
Yeah, very interesting. I'm looking at the same code on Polar Signals Cloud, and the switch case is only shown as like the switch statement, but the individual cases aren't highlighted. It's then just what's within the actual case that's highlighted. So it's definitely a different form of like showing it in the code as visualization. So I think it's not perfect here what you had opened.
Yeah, makes sense. All right, so what did we want to do? We wanted to do this switch outside, so we can do this and that. Yeah, so we're gonna start with this, but we're gonna do not left, we're gonna do dict. And then we're gonna do dict bitmap, I guess. Something like that. And then let's make this a uint32 so that no conversions need to happen. And then we can do the exact same thing for strings.
Oh, that would be interesting to profile now, but like in line 20 to 20, you still have the typecasting that we want to get rid of. But I'm not sure, does that make in the add? You still have the uint32, right?
Yeah, and I actually now see why we didn't do this. The value, this requires so which this the if this we always have to call. So it's better for us to not do the type conversion here than here. So actually this made sense. Like this.
There's only one solution. We need to rewrite all of the bitmaps into using ints. Yeah, I can see it now as well, now that you say. Still, like I guess, like, given we only check all the individual values, the type conversion shouldn't happen that often now as well. Just like the equals checking, so
yeah,
might not be that bad anymore.
So now what we have is a bitmap of which items in the dictionary match. And now what we want to do is we want to figure out, we want to, now we don't actually need this anymore. That's pretty cool. We don't need this type switch at all.
Yeah.
That's neat. So
we still have to check for nulls though, right?
We still have to check for nulls, yeah.
Like an individual row can still be null and not point to anything in the dictionary. That's why we still have to check it.
Yeah, exactly. Yeah. So now we do this exactly. We check, does our bitmap contain the value that we would get at this index. And get value index is an int. Yeah, I suppose this is the best we can do. All right. We added. Yeah. I think this is it. Let's see if this already is faster. I don't actually remember the numbers. So we shall see.
It's been too long. Oh yeah, looking at the nanoseconds per op, it definitely got faster. No, I have no idea.
It actually got slower. This is interesting.
Really?
Huh.
Because we looked twice? No.
This is why we do benchmarking. Let's have a look.
So we end up at, well, nothing gotten better, and we can just ignore this. Also, a valid result of profiling. Maybe it was already pretty good. Let's see.
So it looks like that the contains is quite an expensive call. Oh, whoops.
Yeah, I'm gone.
Lost
I'm a flame buff now.
Yeah, so this is quite expensive, it seems. So it needs to perform a binary search. Okay. I wonder. So we know that the result of the bitmap, and it can be at most as many items. So roaring bitmaps are kind of interesting because they can kind of be what you insert can be like anything in the UN32 range, right? But we actually know that we're looking at numbers between 0 and n, right? And so I think something that we can do a little different here is,
with n being the number of
rows.
Unique values within the dictionary.
You're right. So
right, so it's even smaller.
Which in practice is probably much smaller. Yeah, exactly. So in practice, it's much smaller. So we should be able to just extract, basically turn the roaring bitmap into just a normal slice of Boolean values, basically, right? I don't know if there's an API for this, but let's have a look.
Which one are we using again? Is it the... Yeah, it's not the official one, right?
It's
the roaring.
This one. No, yeah, we are using that one.
Oh, we are?
Yes, we can see that in the here in the profiling
Oh, yeah.
data. So there is. What is the difference between? What is a bit set? Zero value of bit. Okay, so a bit set. A bit set. So this sounds right that we want a bit set. And we want to know, where is it? At a certain, if a bit is set, where can we see that? Is there an API for that? Is flipping? I'm confused. Why is there no? Why is there no API for reading this? What? Am I blind? We can insert, we can intersect. It's gotta be read at some point.
Would be pretty useless otherwise. We get like a boolean back. Test whether bit I is set. I just looked at like where do we get booleans back? That's
okay.
that's so freaking weird.
I mean, I guess it's actually it's the correct term now that I.
Yeah, I mean, looking at the implementation, I think that's what we want. It's also like the first one, like looking at the source code of the bit set. It's like a constructor that creates the bit set called new, then the capacity, and then that's the one they already have. And the next one is set and clear. So at least judging by how they structure the code, I think this might be it. I don't know if this is like a normal term for bit sets, but
I believe so. 2-bit set.
But test, interesting.
Is a newer API? Oh yeah, added in 1.7.0. We might not be on a new enough version for this.
But that is for the.
Wow, we are super behind.
Yeah, we are super behind. I saw that the other day.
Okay,
I don't know what happened there.
Let's update this thing.
We don't have renovate bot for FrostDB, it seems, do we?
Yeah, no, we don't.
Maybe we should change that.
Great way to contribute.
Yeah.
If anybody wants to.
I can open an issue on the site.
Yeah, go ahead. Okay, so 1.9 is the most recent version. We found is it .0? Yeah. Okay. Now let's just make sure. bit set is unused, so now we can do this uint, I think. Bit that. Okay. Before we do any other benchmarking, I just want to make sure that we didn't break FrostDB. Whoops. Include block and filter. Okay, we might have. Maybe something to look at separately. I don't think we use growing bitmaps for that. I think we use just Parquet block metadata. So let's try this again. Let's say that looks higher. Let's have a look though. Okay, now we got about 8% faster. I'll be honest, I kind of expected a higher return. It's not nothing, of course, but interesting. This is why we profile. Let's pull up another.
Especially given we only have one single value in the dictionary for the benchmark, right? Like this should be so much faster.
Okay, so now adding is the big one. So this is an interesting one because I think this is something that we can technically optimize in all of our filtering.
In what way do you mean?
It's the optimization that I mentioned earlier, that most of the time we're gonna add the same things. Things that are following each other are most likely either going to be filtered or not filtered, right? And so adding ranges, if there's I believe, because that's how roaring bitmaps work under the hood, I would think that it's possible to add ranges. So given that this is by far our biggest span here, I think this is what I would tackle next. Looks like testing is super fast now. Get value index, we're always gonna have to do this. Array.length, this is an interesting one. Okay, and is null, we're always gonna have to test that. So yeah, I think trying to figure out full runs is the next best optimization that we can do here. Let's have a look at the add range. Nice. That's exactly what I wanted. Okay, so the way this is then gonna work is that we do let's see. match things. And we're gonna do, I think it was a, what is it? 64. This might be difficult because what if we never matched anything?
Yeah. In this case, an int64, setting it to -1 to indicate nothing was set.
Yes, but this API, the
reasonable or
add
something.
range API, it wants a UN64.
Right. Yeah.
Okay. Maybe we just let's figure out all the edge cases, and then we can figure out if we can maybe do something different for that. So we want to figure out the runs at which things stay the same, right? And then we add those ranges. And this is actually interesting because this sounds a lot like run length encoding. This is where that run length encoding optimization would also hold. Quite interesting. And actually, all we need to do for this to still work is just test that whether the first one matches or not.
Yeah, because like the UN64.0 is kind of special here, right?
Yeah.
Yeah. But we also need to, I guess if something doesn't match, we know the previous one still matched. But that seems a bit risky as well. Like I'm almost inclined to say like we just have two variables that we set.
Yeah, maybe.
Start and range. Start and end of the range.
Let's see. The end, both of the ends are actually tricky here, right? So actually we need to track this anyway. Previous and we do so if the if this one is tests true and the previous one not, then we start a new sequence, right? Yes. The previous one wasn't. Okay, so here we can start with 1. All of this only works, of course, if we go to do it here and go 0 range. All right. We'll care about that later. So if the previous one wasn't, we start a new one. But if the previous one was, and the new one isn't,
then we need to add the range.
Then we need to end the range at the previous one, which means that we should probably nest this actually, so that we can do this. Now, is the second one included or no? No. Okay, so this is exactly how we want it then, right? This is exclusive. This is inclusive. All right, that's good. Awesome. Now, we need to still, so we need to now handle 2 edge cases, right? The start and the end. So the end is if and we actually need to add the previous. So this so that means that if previous, then we need to add that last one. And now we need to handle the beginning correctly as well. So actually we might have already. Because we're already handling it correctly, because we start the run with 1 and we do this test. This is the important one.
So if the first one matches, but yes, so at 0, index 0 matches, but index 1 doesn't, we add the 0.
We should probably add some unit tests for this.
Yeah, 100% we should.
But this looks right to me. I think this is correct. But we'll
if the first one doesn't match though, That's the previous check, right?
That's
Two,
why
three,
we still
four.
have this.
Yeah.
If it doesn't match and the next one matches, then we go in here and then we add the correct one. Yeah, I think, yeah, this is correct. This is correct. But we'll still add unit tests. So now let's do our benchmark. All right, that's pretty significantly higher. I think we've now, I mean, we are testing a very extreme case, right? But it is a case that we see a lot in production.
Yeah, very few values in the dictionary. Yeah.
Yeah. Within one record, right? Because they do get chopped up. But yeah. All right. So Matthias is a flame graph for a second again. And we can now have a look. All right. This seems to be getting smaller and smaller. But yeah, so now we can see get value index is pretty much dominating this. And I think we're not going to get around having to read the index of the thing that we want to filter.
I don't think so.
I think the only way that we could get this to be faster is to read all the values at once. But then we have this, like, it's kind of a slippery slope because
reading all the values at once, I'm not even sure that's going to work because we then would need to XOR it with like the null values or something. Like, yeah, I don't see how that could like how that could actually work.
Oh, that's actually an interesting thought. What if, oh, I like the way you think.
Everything is a null.
What the null values, we continue them, right? So that actually makes that means that we could build a bitmap of the nulls
and XOR that bitmap with the
and it with the
X and it. Because it has to it can't be both in the resulting bitmap and in the XOR bitmap. No, it can only be in the resulting bitmap and not be in the null bitmap.
That depends on how we build the bitmap from the nulls. I was suggesting that
the other way around. I see.
We
all the none values.
We set a bit for the ones that
yeah, I was already for the ones that are valid, but like I was already thinking. I think at the arrow implementation, it sets a bit in its internal bitmap for those that are null. Pretty sure it does it that way around. So that's basically taking everything that matches and then excluding those that are null from the bitmap. But
yeah. So yeah, that's the way that I would have built it as well, because then we can end that bitmap with our resulting bitmap. Because anything that is null would then be 0 in the null bitmap, and you know,
No, it's the other way around. All the nulls are 1 in the in the arrow bitmap.
Ah, is it? Okay.
Yeah. So that's why I'm saying, like, we have all the indices in the bitmap that match, and then we have the ones that are null, which are also 1. So we need to, like, if they can only be, yeah, it's like an not intersection, it's like an remove everything from the resulting bitmap where it's 1 in the null bitmap. What is that? Left XOR? No, I don't even know. I think we're getting ahead of ourselves,
Yes.
maybe.
This is actually interesting.
But it's interesting, yeah.
I didn't pay attention to this earlier. The bit set is actually implemented in a separate package. I just randomly saw that in the.
Yeah, it's like an entire different repository.
Yeah, I thought it was part of the Roaring Bitmap repository. That's an interesting one, because I do have to wonder if Roaring Bitmaps actually make sense for this kind of case, where we have, you know, 0 to n values in the bitmap. It seems like maybe that's not the best. It might not actually be the best thing to use, but I mean, now it seems like we're not actually spending pretty much any time in Roaring Bitmaps anymore, so probably it's not valuable to optimize there.
No, probably not.
Anyway, I think we could have a look at the null, but other than that, I think you know, it's very obvious that get value index is the only thing that's really still dominating this whole path. So yeah, and we would have to do a type specific like what we could do is that we read all the values of all the indices all at once, but then we're leaving the safety of our like arrow allocator that's limiting the amount of memory that we can use in a query, and I don't know that I like that.
Yeah.
And by the way, just because I'm kind of thinking out loud already, the Roaring bitmaps, even though, you know, they're probably very, very small, but they are actually outside of that memory that we're allocating through the arrow allocator. So it is technically, you know, a little bit of an unknown piece of memory that we may be using in our queries. For those who don't know and are watching on the stream, basically we have this super cool concept of allocators in Apache Arrow, and it's very ubiquitous in FrostDB, and it allows us to do something really cool, which is a really hard problem in databases, which is that we can limit the amount of memory that a query can use. And as opposed to ooming the entire system, we can just say, hey, sorry, this query is actually using more memory than we allow it to use. And so that's really, really cool about you know, Arrow and FrostDB together. And so that's why we don't like it to kind of go out of that safety. So yeah.
Yeah, I'm looking at the Arrow code right now, and where they have the their bitmaps, because I think what you're saying makes sense, and I think what like the Arrow, like the bitmaps inside of the Arrow package, what they do, they use that memory allocator to allocate buffers for the bitmaps. So maybe we could kind of either expose the bitmaps that like Arrow internally uses that also use the same allocator, or we just like fork it and make it a kind of first-class citizen in FrostDB, where we use those Arrow bitmaps and helper functions to set and unset, etc., Yeah, just to
makes sense.
yeah. I'm just trying to find it in the code where that code lives. Looking at the array packages. Maybe I can find it, but not too important for the stream, I suppose.
Yeah, but yeah, interesting thought. But yeah, let's the only other thing that I could think of, what we could do is that we do something that's very limited in the amount of values that we're reading. Let's say, 128 values or something like that. Something that definitely fits onto the stack that's not one by one. You know what I mean? But we would need to make sure that that we can do some sort of batch operation on these value indices, which I'm not sure we actually can. So we would need, again, we need to go to the array package.
I'm literally looking at the same one right now. If you want to, we can like quickly look at what Arrow does for the bitmaps internally, because it's not that complicated. It's pretty neat.
We can have a look at that in a second. I just
Sure.
I quickly want to have a look at like I don't know, like a uint64, for example. Can we read? No, I know this is a builder. Sorry, so we can read all values, but we can't read a pre-allocated slice of values. It seems like that would be a reasonable addition, right? Say something different than just value, that we do values where you pass in an array that
of indices, like,
no, it would be a range.
okay,
so
yeah.
you need to pass you need to pass a range of indices and then a slice of exactly the same size, and then it would write those values into that slice. I think this would probably be the right solution to batching, getting values out of the arrow array into that slice. And the reason why this is useful and interesting, I think, is because, and this is kind of something where a language like Rust or C or C++ have a little bit more control over these kinds of things. But the reason why this would be useful in Go is if we have a constant sized slice that we can work with that is smaller than a certain size, and I think it's like 64K or something like that, then it ends up on the stack. And the stack is just generally much faster for us to access than anything else. And so I think this is why this could make sense. It probably makes sense to write, we can maybe do the next Let's Profile about this, but it would obviously make sense to first benchmark it, do it on one example and figure out whether it actually would make a difference. So yeah, I think we've kind of exceeded, I think, the amount of time that I could spend today, but I don't think we actually ran the bench stat, and that's the kind of result that we wanted to see. So we got almost 50% faster with the most recent changes. So that's pretty cool. I'm quite excited about that. Yeah.
Yeah, I agree. And this is only for the array equal scalar, so we can adjust those, and like all the other dictionary, like not equals, etc., they can get faster as well.
Yeah.
So
yeah, we can apply exactly the same optimization to a lot of these, and it looks like the biggest one is actually the one to add ranges to
mm-hmm.
to the bitmaps, right? That we don't individually add to the bitmaps. Looks like that's really a really big one for us that we should be doing throughout the filter query plans.
Yeah, I guess that's like part of like what makes especially the roaring bitmaps, right? Like I think that's a selling point of the roaring bitmaps here, because like they're like looking at what Arrow has internally, it's just a bitmap. So I think if we are going down the route of, or if we continue using roaring bitmaps, I think what you said makes total sense, that we utilize the ranges the most we can. Yeah, 100%.
I mean, I think there's probably a lot that we could do to optimize the kinds of bitmaps that we would be working with here, because we don't have this very general case like roaring bitmaps do, where we only deal with n amount of rows in an array. Whereas roaring kind of needs to work with the entire like UN32 space.
Yeah.
So yeah. All right. Cool.
Yeah.
Well, yet another successful Let's Profile. It didn't necessarily go in the direction that I expected. But this is exactly why we do profiling. This is why we have to look at the data and let the data guide us. So yeah, awesome. Thanks everyone for tuning in, and hopefully see you again next time. Have a wonderful local time.
See you soon, everybody, and reach out on social medias, etc. if you want to follow up or just discuss. Thanks everybody for hanging out in chat. Nicholas, you're still here. I don't know if anyone else is still here. And I mean, I see a minus 45% delta on the screen, so I think we were successful. But yeah, see ya everybody, and hopefully see you sooner than this time around. All right, take care.